Hi guys, so in this video we will discuss the part 2 of the static forces. So let's begin. So one of the topics that we will discuss under statics is friction. So what is friction? Friction refers to the resistive force that arises to oppose the motion of an object past another with which it is in contact. So this is the force that resists the the motion of a certain object which is in contact to other material. So basically there's two types of friction: the kinetic friction and the static friction. So first, the kinetic friction is the resistance an object in motion experiences. So when an object is already set in motion and it experiences friction, it is called kinetic friction. And then we have this static friction, or the resistance that a stationary object or a non-moving object must overcome in order to be set in motion. So uh, prior to any movement or motion, there is this static friction, a resistive force that object must overcome before it starts moving. So the coefficient of friction is one of the important parameter that the or important factor that is used in the computation of friction. So the coefficient of friction is the constant of proportionality for a given pair of contacting surfaces that relates the frictional force between them to the normal force with which one presses against the other. So the frictional force is dependent on mainly these two items. So first one is uh, the kinds of surfaces that are in contact. So this depends on the the properties of for example the two materials the that are in contact prior to the motion. So may it be yeah, or is it or I should say the degree of smoothness or roughness determines the frictional force. And then the second one is the perpendicular force. This is the amount of force with which either surface is pressed against the other. So that amount of force that press. So what is I mean the the quantity or the intensity of that force that press against the other surface that in contact uh, is also one of the factors that affects the frictional force. So let's move on to the static friction. Um, so basically, the static friction Fr, the frictional force, is equal to the coefficient of static friction F multiplied by the normal force N. So as you can see in this illustration, so there is this object at rest which is pressed against the floor with weight W and a corresponding normal force N. So if this object will be moving in this direction, there will be a corresponding frictional force in the opposite direction. So as we have said a while ago, the static friction is used if the body is not moving, and kinetic friction is used if the body is already moving. Alright. So we now go to the um, this illustration. So if a certain force F pushes the object to the right, like what is shown in this illustration, there will be the frictional force that is opposite the direction of F, and of course the weight W, and in this direction of motion. So, in this scenario, the summation of forces uh, in horizontal is equal to 0. So, F will be equal to Fr. And then the summation of forces in vertical is also equal to 0. That's why the weight W is equal to the normal force N. Now, if a certain force is applied to the object at a certain angle theta, so a while ago the force is a straight horizontal force. Now, for this direction of motion, what if there's a force uh, that, that is applied at angle theta to this direction? So, in this case, the summation of horizontal force equal to 0. So, the frictional force Fr is equal to the F cosine theta, because of this adjacent side. You need to you need to determine this adjacent side, which is F cosine theta. And for the vertical, the normal force now is equal to W, which is in opposite direction, plus uh, F sine theta, the corresponding component of F uh, for uh, for the vertical side. So, if the block is inclined at a certain angle and the block pushes a certain force horizontally, like what is shown in this illustration, so there's the force inclined at angle theta, the weight, the downward force caused by the weight also has an angle theta from the inclined object, and then a corresponding friction force that is in direction of this inclined floor. So, given this illustration, we can now project this illustration through a free body diagram. So, given the x and y axis, we now have a normal force directed upwards, and then the weight at the angle theta, the force with the downward force at angle theta, and then the opposite friction force. So if the block is inclined, as we said a while ago, following the condition of the summation of forces in horizontal and vertical, F cosine theta now, which is this one, so F cosine theta, which is the horizontal component, is equal to Fr, or the frictional force of the opposite direction, plus the weight cosine beta. So beta is the angle, the other angle, the other adjacent angle of theta. So beta is equal to the 90 degrees minus theta. So for the vertical, we have now uh, the weight W sine beta for the vertical component of force plus F sine theta is equal to N, the normal force. So that's it. We also have this belt friction. So for this illustration, given two forces, two tension forces, no? So F sub 1 and F sub 2. So if we have tension force F sub 1 and F sub, sorry, this should be F sub 2. This should be F sub 2. So given this force with the direction to the right, uh, um, the formula or the equation in solving for friction is then F sub 1 over F sub 2 is equal to E raised to F theta, in which F1 and F2 are the tension forces, and then F is the coefficient of friction, and theta is the angle of contact in radians, and then E is equal to 2.71. So there's a friction here at this angle, and that is the one that is being computed in this equation. So let's now go to the parabolic cable. So assuming that the load is uniformly distributed along the horizontal, following are the useful formulas for same elevation. So same elevation meaning this parabolic cable has the same elevation like this one, the elevation of this one, and the elevation of this one has same elevation, and then that the uniform load is distributed along the horizontal. So the best example of this is a horizontal bridge that is being supported by a parabolic cable, as you can see in most bridges. So for this um, for this diagram or illustration, we can use the following formulas. So let's say H is the tension at lowest point or the minimum tension. H now is equal to the unit weight multiplied by the square of length over 8D, which D is equal to the sub of the cable. So this is the sub of the cable. So given this illustration, so this is this this is now the H. This is the tension. This is now the tension at the lowest point, and then the W, the corresponding weight of with this kind of illustration is W is equal to the unit weight W multiplied by the length over 2. Next, for the tension at the supports, for the tension now at the supports, the maximum tension at the supports, T is equal to the uh, square of the weight plus the square of the tension at the lowest point. So this is derived from the force triangle, which at angle theta, this is the tension force at the support given the weight, and then the tension, the other tension at the lowest point. So given the equation for weight that we've shown a while ago, T now is equal to the square root of W L over 2 squared plus H squared. Length of cable. So, if we estimate the approximate length of the cable, this length of the cable now, S, is equal to the length plus 8D squared over 3L minus 32D raised to 5 over 5L raised to 4. And a factor of safety is equal to the ultimate tension of cable, as we have shown by the equation a while ago, over the tension at the lowest point. So these are now the formulas uh, for supports in case the parabolic cable has different elevation. So we have the formula for the tension at lowest point, and then the tension at lower support, and then tension at higher support. So there will be a tension at lower support and tension at higher support, since they have a different elevation, right? And using a parabolic equation of or proportion of second degree equation, we have the length of one squared over the sag is equal to the second length squared over the second slug B. Okay, so, and then the cable of length is equal to S sub 1 plus S sub 2, in which S sub 1 can be calculated with this equation, and S sub 2 can be calculated with this corresponding equation. Now let's go to the catenary. So consider a cable uniformly loaded along the cable itself. So the difference of the catenary with the parabolic cable is that um, the cable itself has the uniformly loaded weight instead of uniformly loaded weight along the horizontal like this. So this one, the uniform load is distributed along uh, along the unit distance per unit distance of the cable itself. So a good example, this is like for example, we have a hanging chain at for a certain that we can see in the parking areas, no? Those have uh, a uniform load like this shown in the illustration. So um, given this illustration, um, we can now see that for this catenary, there's the tension at the highest um, or at the upper support, and at the lower or the lower tension, which is T sub O, and then C now is equal to the corresponding distance from the origin, from this origin up to the lowest point of the cable. S is the distance of the cable, and W is still the weight, which is equal to the unit weight multiplied by S. Now, so with with this force, such as weight is equal to the unit weight times S, we can also consider that for this tension at the lowest portion, at the lowest portion, we can say that this T sub O is equal to the unit weight that is being projected in this direction multiplied by this distance of T sub O. Uh, I mean this distance from the origin to the uh, lowest point of the cable. So if that's the case, we can let P sub O is equal to WC, in which we can use which is will I mean which will be useful in deriving our equation. So here now, using the force triangle again, we can see that for this angle theta, corresponding theta here, no, theta, and then the weight W, which is equal to unit weight W times S, and T sub O, which is the tension at the lowest point of the cable, we can write this equation. So T squared now is equal to T sub O squared plus W squared, and is now equal to T sub O squared plus W squared, and multiplied by S squared, since it is equal to W. And then using, as we said a while ago, if we let C is equal to T sub O over W, we can now arrive at this equation. So this will be our first equation, or second equation. T is equal to W multiplied by the square root of C squared plus S squared. Since our first equation is this T sub O is equal to W times C. Now, uh, from that derived equation, which is T is equal to W multiplied by the square root of C squared plus C squared, we can we can now uh, we can now um, say that T is equal to WC times the square root of 1 plus S squared over C squared. Why? Since we divide we when we divide both sides by C squared, so this now will become this this will become 1 plus S squared over C squared. All right. So I hope you get it, no? So C squared plus S squared, when we multiply uh, by C squared over C squared, so we will have WC, the square root of 1 plus S squared over C squared. So since WC is equal to T sub O, T now is equal to T sub O multiplied by the square root of 1 plus S squared over C squared. So we now have the relation of the tension T to the tension T sub O and S and C. Now, um, when we when we get a portion of this distance s and get the uh, unit measurement such as the ds, dy, and dx, um, and relating it to our force triangle, we can now say that dx is equal to ds cosine theta, right? So dx now is equal to ds um, in relation to the force triangle. Cosine theta now is equal to t sub o over t. Then dx is equal to ds, and then the correspond and then as we remember, t sub o is equal to cw, and t is equal to this equation, uh, which we uh, which we uh, which we write for this value of t. So this is further equal to ds equal to t sub o over t sub o square root of 1 plus s squared over c squared. And then if we um, so we cancel t sub o, so dx now is equal to ds over the square root of 1 plus s squared over c squared. All right. So integrating now dx is equal to ds over the square root of 1 plus s squared over c squared. uh, we can now write the integral of dx from 0 to x is equal to the integral of ds over the square root of 1 plus s squared over c squared from 0 to s. So in this integration, we will get x is equal to c uh, times the inverse hyperbolic sine of s over c, which gives s over c is equal to hyperbolic sine of x over c. So we can now have this. We can now arrive with the relation of s to c. So s now is equal to c hyperbolic sine x over c. Now, following the same illustration, which we got the the unit measurements of dx and dy, we can now relate that tangent theta, which is um, tangent theta, is equal to dy over dx. So we can write now that dy is equal to tangent theta multiplied by dx is equal to the corresponding weight w over the the tension at the minimum support, which is t sub which is t sub o multiplied by dx. So um, further computation, we will have dy is equal to w over t sub o dx is now equal to ws over cw dx and equal to s over c dx equal to c hyperbolic sine of x over c all over c dx. So we will come up now with this dy is equal to the hyperbolic sine of x over c dx. And following the the method that we used a while ago, we can now integrate dy uh, from this distance c to y, which is the distance of the sag. I mean s, or the distance of the cable s, and we will come up with this equation. So the integral of dy from c to y is equal to the integral of, of hyperbolic sine x over c dx from 0 to x. So as we go along with this computation, uh, we can arrive at y is equal to c multiplied by hyperbolic cosine of x over c. All right. So since we have now the equations for y and s, how can we now relate y and s? So relating the square of y and s as shown, we will get this the following equation. So if y squared minus s squared, it will be equal to c hyperbolic cosine x over c squared minus c hyperbolic sine x over c squared. So y squared minus s squared now will be equal to c squared, the square of hyperbolic cosine x over c minus the square of hyperbolic sine x over c, which is equal to 1. So this equation, the value of this is equal to 1. So we will have now y squared minus s squared is equal to c squared. So we have now related y, s, and c. And as we remember, that t is equal to w multiplied by the square root of c squared plus s squared. We can now uh, we can now uh, write from y squared minus s squared is equal to c squared that t is equal to w multiplied by the square root of y squared, and therefore t is equal to uh, the unit with w times the distance y. So that's all for now, guys, and hopefully we can continue with the solve problems for our next video. Thank you.